I think open questions in fundamental physics are still worthwhile to be pursued. But I don't really want to go into the details here, but would like to use that slide to make the point that mankind really in the past decades has put an effort into developing tools, technology, and projects that enable us to study open questions in fundamental physics. For example, at CERN, big colliders we're using to really reproduce conditions that must have existed at the beginning of the universe to study everything. What I would like to show you today is that I think there is an emerging new technology which could help us to complement our portfolio of technologies and tools to tackle these open questions in fundamental physics. And it is quite telling that we have been last year celebrating 100 years of quantum physics or quantum mechanics. It really goes back to these gentlemen and many more at the beginning of the 20th century to develop quantum mechanics, a very impressive development at the time. But then it took several decades for that theoretical framework to translate into real-world technology spin-offs. The first one is the transistor, then came the hard disk, and the laser. So this is what people refer today as the first quantum revolution when it comes to technology. I think we have very good reasons to believe that we are in the midst of a second revolution, which is mostly driven by the enormous success we are seeing in quantum sensors, in particular the development of atomic clocks, but also atom interferometry, and now reaching into the maturity levels also of quantum computing. This is what people refer to as the second quantum revolution. This is now when these technologies really become ripe for real-world applications, but not only real-world applications, but as I would like to show you, also applications for the exploration of fundamental physics. And back to my shopping list, I would like to use one question in particular, even though all of those could be addressed with quantum sensors, to show how these quantum sensors could help us to answer this question. And the question I've chosen is how gravitational waves tell us about the universe and its fundamental laws. So let's start out with that question as an introduction. When I was saying that the last 100 years were a century of quantum mechanics, it was also actually a century of general relativity, to be very honest. And according to Einstein's theory, gravity is not a force, but it really relates to the curvature of space-time. And to put it in the words of John Wheeler, matter tells space how to curve, and space tells matter how to move. Therefore, massive objects, and this is postulated in general relativity, will generate ripples in space-time. And one of the experimental challenges was to develop technologies which would enable us to measure these very small ripples in space-time very, very precisely. So this is how these ripples in space-time could be generated. That's an example of a video which comes from LIGO, gravitational waves. So you have two massive objects, potentially two black holes, which are starting to dance in each other. And while they are starting to be in their gravitational field and potential, they are sending out these ripples of space-time, these gravitational waves. And if you wait towards the end, you can see, because these waves carry energy, and therefore the objects are coming closer and closer to each other. And eventually at the end, they will merge because energy has been released in terms of the gravitational waves. And this is what's coming here now at the end. This is the final merger of the two black holes, if you like, which then basically gives you the final ripple, the so-called spark and spurg at the end. So this is when the two objects are merging. And these are when gravitational waves are being generated. To the next slide. Now, let's go back 1.3 billion years ago. There was a particular merger of two black holes. And that was actually the first observation of a gravitational waves, which started 1.3 billion years ago. There were two black holes, as you can see here, starting to merge. And they had roughly 30 solar masses, so 30 times the mass of our sun, each of those black holes. So the total mass of the merger was 60 black holes with the different radius. So you basically can calculate now that the impact such a merger would have on Earth, an instrument of Earth, because of the length dilatation, it will change is at the level of 10 to the minus 19 meters. Now, what is actually 10 to the minus 19 meters is a quite impressive number. And that was the first thing I was looking at in 2016 after the discovery to see if there's other alternative technologies we can develop to do this. So how do we get to 10 to the minus 19 meters? And what do 10 to the minus 19 meters actually mean? Quite impressive. Let's assume this line here is 1 meter as our reference. Then I'm dividing this by 10,000. That is roughly the human hair, 100 microns. I divide it again by 100, then I come to the typical wavelengths of light. I divide again by 10,000, and then I come to the atomic diameter, which is around 10 to the minus 10 meters. I divide again by a factor of 100,000, and I come to the diameter of a proton or a neutron, which is at 10 to the minus 15 meters. I divide again by a factor of 10,000, and then I finally reach the mass scale of, the length scale of 10 to the minus 19 meters. And that's the level of sensitivity an instrument on Earth needs to reach in order to measure a gravitational wave. This is pretty impressive. So if you think of a variation which is much smaller than the diameter of a proton, that variation you need to be capable of observing to see a gravitational waves. Quite rightly so, because of that technology development, these three gentlemen, for the observation of gravitational waves in 2016, then became a Nobel Prize. That was mostly for the development of the technology that enabled us to make that measurement. It was not for the theoretical invention, because that's general relativity. It was for the technology development. And today we do have a quite diverse laser interferometer observatory across the globe. It's LIGO, Virgo, Kakra. These are laser interferometer experiments which are today able to measure gravitational waves at the level of 10 to the minus 19 meters and even better. And because of that observation, I think we now have very good reasons to believe that we can use gravitational waves not only just to detect them and prove general relativity is right, but we can really use them now as a tool to try to understand what kind of information do they carry from the beginning of the universe. And there's in particular a very interesting frequency range, which is basically around here, where a lot of interesting phenomenology must have been carried by gravitational waves when gravitational waves were generated at the beginning of our universe. So if we can be able to build instruments that give us access to this frequency range, we can use gravitational waves as a tool to understand what really has happened at the beginning of the universe. Very similar than what we're doing at colliders at CERN, but with a different technology and a different tool. So this is now that frequency range I was just mentioning. It's typically 10 to the minus 6 to 10 to the 4 hertz. So it's a very large frequency range. And today we have basically one category of experiment, Earth-based laser interferometers, which can carry that frequency range. So this is LIGO, Virgo, Kakra. That 60 solar mass merger was the first observation of a gravitational wave. And the future program is actually already being defined. So there is LISA. It's a space-based instrument with 3 satellites. It's meant to fly in 2035. It's already under construction. There's a lot of discussions about building on Earth more precise laser interferometers, like in Europe, the Einstein Telescope, or Cosmic Explorer in the US. So there is a broad and very interesting program that is currently under development. But one of the things I noticed in 2016, and this is, as we would say in London, mind the gap. If you ever have made it to London, you see the tube, mind the gap. There's an interesting frequency range which seems to be inaccessible to laser interferometry. Now, if you were able to build atom interferometers at the kilometer lengths, you could fill in this frequency range relatively easily, and you can tune even the frequency to which you would like to have. So this is the sensitivity of a kilometer scale experiment, which would match the one of LIGO Virgo, which are 4 kilometers. And you could even think of pushing this further. So laser interferometry can be complemented with atom interferometry, which is one of the quantum sensors I would like to introduce to you to really fill this gap. You can even push it further, and if I have a bit time, I can tell you about this, because we have been developing a space-based concept of how to bring that technology into space and push even further the sensitivity level. And we have baptized this experiment EDGE, but it can really then outperform in the future a very large range of that with the frequency range in the middle. So why would we like to do this? The reason why we would like to do this pushing of instruments, and I will give you two now, one is the first one here, is that if you really look carefully what these instruments can do, and that's being best shown here. So this is now the merger mass of two black holes, for example. So that it ranges from 10 solar masses to 10 to the 6 solar masses. If you translate what LIGO today can do, and we're around 100 solar masses, as you can see here. So this is LIGO, that's what we are measuring today. But more important is what type of redshift can we achieve. Now, redshift is a measure of how far can I look into the beginning of the universe, how close are distances I can see. So I give you another scale here. So this is the age of the universe. If you are a redshift around 10, you basically start being sensitive to 300, 500 million years after the first star. So this is the first stars. But if you really want to understand the beginning after the Big Bang, you will have to push your instrument up to beyond 1,000 in redshift to really go at the beginning of the universe. And this is what these space-based atom interferometer experiments are capable of, and this is what we are predicting. It will really push us into the domain where the exploration of gravitational waves that were generated at the beginning of the universe, therefore carry a lot of information about the beginning of the universe, is possible. At the moment, we are really just scratching a couple of million years in our universe, which is interesting, but not fundamentally interesting as far as I'm concerned. So one of the real goals is to go back here. We want to go back at this beginning. We want to understand what has been generated there. This is what we're doing at CERN, for example, when we are building these big colliders and accelerating protons to smash them together at the highest possible energies, because then we are creating conditions which must have existed at the beginning here. And today we are exploring at colliders like the Large Hadron Collider 10 to the minus 10 seconds after the Big Bang. But with gravitational waves, it can even go much further if we have the instruments to build that. So that's the long-term goal we are trying to pursue here. Another interesting, and that's the second reason why this mid-frequency range is so important, another very interesting aspect of this mid-frequency range is the fact that in the mid-frequency range, you can observe astrophysical signals, not just like the last chirp we are doing in LIGO, which is a fraction of a second, so you have a signal of a fraction of a second. In the mid-frequency range, with an atom interferometer, for example, you can observe signals which have a lifetime of days, weeks, and months. Now, if you can see a signal for days, weeks, and months continuously, you can use the rotation of Earth around the sun to triangulate exactly where the signal comes from. Now that will unlock a completely new world of multi-messenger physics, as we call it, because you will have the capability to tell other instruments, telescopes and everything, saying, in 5 days from now, there will be a big merger coming your way, make sure you are observing it. So the multi-messenger physics we will be able to do with the mid-frequency range is unprecedented and will open up a completely new way of doing physics at the moment. So it's not only gravitational waves, you can also then have electromagnetic waves, you can have neutrinos, everything coming together to learn about this cosmic event that has happened and was first detected in the mid-frequency range. That's another very interesting thing. So now how can we really, on the technology side, unlock this fantastic, on paper, potential? For that, we have to go back to laser interferometry and understand again how laser interferometry is being done. So in laser interferometry, this is the LIGO experiment. You basically have two laser beams which are orthogonally being shined on a beam splitter. They take two different paths. One path now hits a mirror. The light is being reflected. It comes back to the beam splitter. And the beam splitter then basically makes this into the detection region, the interference patterns. And now what you can see here is when there is a little length variation coming from gravitational wave, as you can see here, this 10 to the minus 19 meter variation, that will give me a change in the interference patterns here because of the laser light now interfering differently, and I'm measuring the laser light interference patterns at the level of 10 to the minus 19 meters, which, as I said, is absolutely incredible, but that's the technology which exists today, and we have been building this over 15 years. So how could we do the same thing with an atom interferometer? Now, atom interferometry is conceptually identical to laser interferometry. Laser interferometry, I'm shining light on the beam splitter, take the two different passes as I just mentioned to you. But in atom interferometry, the only difference is that my active element is not laser light, it's not photons, but it's atoms. And it's not just one atom, but it is a large ensemble of atoms. We are at the moment of around 10 to the 6, 10 to the 7 atoms, and we're trying to push this to around 10 to the 10 atoms in the future. But these atoms are not only just 10 to the 10 atoms, but they're also 10 to the 10 atoms in an ultra-cold state. You can even think of that as a Bose-Einstein condensate, if you like. So they're really ultra-cold, and because they are ultra-cold, they're in a superposition. So they're really starting to absorb the quantum nature. Now, with the help of beam splitters, which I can construct now with laser light, so-called pi-half pulses, I don't want to go too much into the detail, I can start splitting my ensemble of my atoms, half of them in the excited state, the other half stays in the ground state, so I'm opening up my two different arms, and at the end of my sequence, I'm not measuring light fringes, but I'm measuring so-called atom fringes or matter fringes, simply because the atoms are in a superposition, and I'm collapsing the wave function here so that the quantum nature or the wave nature stays the same. So I have exactly the same way of measuring these things. Yes?
I have a very question. When you talk about the splitting, does that actually really mean you split the package into two separate packages
So, yes.
in space, or is it just
Yes, it's also in space. Because what happens here, and maybe, well, I don't have a dedicated slide for that, but what happens here is you have a so-called pi-half pulse. It's a laser beam in which you shine on the atoms, and half of the atoms, because you're tuning it exactly, will get an h-bar kick. So they get a momentum. And because they get a momentum, they will start separating also in space and later in time, in space-time, from my ground state. So you're really opening up an atom interferometer sequence in space-time. Another important sensor I have to introduce to you, because we want to combine atom interferometry with atomic clocks, is atomic clocks. Atomic clocks is truly, today, I think, optical clocks in particular, the only quantum sensor we have that truly has reached quantum advantage. When we're talking about quantum advantage, we mean, is the quantum sensor better than classical technology? And atomic clocks have outperformed classical clocks since more than 5-6 years, and they really have now reached an unprecedented level of precision. For example, in my lab, we're currently building the next generation of optical clocks, and these optical clocks, if I would have started them at the beginning of our universe, 13.7 billion years ago, they would have measured correctly the time today by fractional seconds. Now that is exactly the level of precision I need to go to this 10 to the minus 19 meters, which I mentioned to you before. Atomic clocks do have that precision, but they do not have the capability to really see the interference pattern. So what we need to do is, we need to marry atomic clocks with atom interferometry to really get the ultimate sensitivity we need to go to 10 to the minus 19 meters. And that is the key ingredient of these two atom sensors, which we have been pursuing now in our program for quite some time. This one is not really working too well. I need to be closer maybe. So that's the atomic clock, for example, we're currently building. So that will have that level of precision. And this is how the lab looks like, which I have at Imperial College. You can see the technology we are developing. This is for the atom interferometry. This is for the optical clocks. Now it happens to be, which is also quite interesting, that on the same technology you can build a quantum computing platform, but I don't want to go too much into the details. So these are the two which we would like to combine in one technology to have atomic clock precision, but the capability of doing interferometry with the atoms. One of the important conceptual measurements we will have to set up and to demonstrate, and this is what I'm going to show you here in what we in Germany would call a Gedanken experiment. So I have here in that Gedanken experiment 2 atomic clocks. They've been made out of one species of atom. In our case, this is strontium. It has very interesting properties. This is where you can build the most precise clocks today. So these atomic clocks are really being separated very far from each other in space in our Gedanken experiment. Now what I can do is I can use one common laser beam, the so-called pi half pulse I showed you before, to synchronize these 2 clocks. So I shine this one laser beam on my 2 clocks. What will happen is now that the atoms in both of the clocks, half of them will be in the excited state and half of them will be in the ground state. So this is the ground state and the excited state of my atom species. Now, I let the experiment begin. The 2 clocks now travel through space and time. At the end of my experiment, I have again one common laser beam. Now, what happens if you write down the Schrödinger equation for that problem, you can easily see that the excited state will have accumulated what we call an imaginary phase. That's pretty standard quantum mechanics, and the imaginary phase will be proportional to my frequency difference between ground state and excited state, and it will be proportional to the time of my experiment I have been running. Now, the key ingredient is that I make a differential measurement between these 2 imaginary phases of the 2 clocks. So I compare the 2 imaginary phases, the differential phase between the 2. If nothing has happened, I'll get a null result. Now, what would happen if my measurement clock is now exposed to a gravitational wave? Because of the strain of the gravitational wave, there is a change of length in the space-time continuum, but because the speed of light is a constant, that change of length will automatically translate into a change of time, a delta t. That delta t now is imprinting on my measurement clock on the imaginary phase. So I have t plus delta t. If I now compare this with my reference clock, I can measure back delta t. Out of delta t, I can measure all the properties of the gravitational wave, strain, and frequency. Pretty standard, pretty simple concept, differential measurement with one common system. Now it happens to be, and that's actually quite interesting, that with exactly the same setup, I can also be sensitive to a potential very interesting dark matter candidate, which is an ultralight dark matter candidate, and even more precisely a scalar ultralight dark matter candidate. So the idea here is that ultralight dark matter is surrounding us as we speak, but it is so light that you can't really think of it as a particle anymore, and the way how you would describe it is as a classical wave. So that classical wave is basically surrounding us with a characteristic frequency of delta omega alpha dark matter, the oscillation, which is nothing else than its underlying mass hypothesis. Now, how would that dark matter coupled to our standard model Lagrangian? Well, it's pretty simple. In its simplest incarnation, it will start varying fundamental constants of my atoms. For example, it varies the electron mass, it imprints the oscillation frequency, or it could also vary the fine structure constant alpha and changes the frequency. Now, that variation is again the delta omega alpha dark matter imprinting on my phase. It's now not imprinting on the time part like a gravitational wave, but it imprints on the frequency part. So if I make my differential measurement between the 2, I can measure back delta omega alpha and therefore infer whether or not ultralight dark matter in that frequency range I'm sensitive is present in nature if I have enough sensitivity. So with this setup,
in this case, are the phases put by the gravitational wave and the dark matter degenerate, or is there a way to disentangle them?
Yeah, there's a way to disentangle them. The best way would be directional. You absorb a signal for a longer time. There's different ways of how you could do it. So the dark matter in that category will have a decoherence time. So it will decohere, it will come back depending where I'm measuring. So I have to have longer measurement campaign. Like for a gravitational wave, for example, it's mostly directional, and I know where it comes from. So I can separate these 2 from each other. But even better would be to have 2 different experiments on the globe. to cross-correlate them. That would be, you can do it with a single, but with two it would be even better. Yeah. But yeah, it can be separated. So this is the conceptual measurement. Now, that conceptual measurement and the combining of atom interferometry with atomic clocks needed to be demonstrated. Because that is a new technology which is not existing yet. And for that reason, we went to the UK government in 2018, and we were building a rather big consortium in the UK, which really brings together all of the big UK university players. So there was Oxford University, Cambridge University, we had the Quantum Hub in Birmingham, Liverpool University, we had our National Particle Physics Laboratory, RAL, coming into it. We had King's College London, and Imperial College London was the lead university where we were building the biggest lab. So that collaboration, which we baptized the ION collaboration, came together to really demonstrate these two components. Can we marry atomic clocks with atom interferometry, and can we use it to do this differential measurement and demonstrate that we can see these signals in the differential measurement. That's the ION collaboration as it was in 2021. That was in Oxford. I don't want to go too much into the details, but the point I'd like to make here was, at least for the first time in the UK, but also have not seen it elsewhere, is where for particle physicists like myself, came together with people who are actually developing quantum technology, who knows how to build atomic clocks, who knows how to build atom interferometry. So it was the first time these two communities, which typically didn't talk to each other before, were coming together. And today, in 2026, we do have actually a quite vibrant exchange between these two communities, both on the technology side, but also on the physics side. And that's not only in the UK, this happens now at many different places, as I will show you in a minute. So one of the charges we had to do this R&D program was to build 5 laboratories in the UK to do all the testing we needed to develop the atomic clocks, that marry the atomic clocks with atom interferometry. So that was quite a challenge. So one of my responsibilities as the main PI of the program was to oversee the build of these 5 laboratories. So the Cambridge 2021. So all of that basically was built in 2021 in parallel particle physics fashion, and it's all being documented here. So all of the blueprints and designs, if you want to build your own laboratory, is open source here in that paper. That was one of the requirements. Our grant had to make it open source. The biggest breakthrough actually was published in this year in a Nature paper, and that's exactly the first demonstration of the technology I mentioned to you. We used atom interferometry on the atomic clock transition of strontium, which is the optical clock. For the first time, nobody ever had done atom interferometry on the optical clock transition. But not only we did one atom interferometry, we really did also the differential measurement, as I mentioned to you. And in order to demonstrate that this would be working, we have been injecting a hypothetical dark matter signal in various different frequency ranges to demonstrate that you're not dependent on the frequency to measure it back. I'm not sure you can see this, but the red curve is the true signal we injected. The black curve is what we have been measuring back in the atom interferometer differential measurement. So this is the 2 clocks making the differential measurement, but now with 2 atom interferometers. So it's the first time that that technology has really been demonstrated completely. Yes, please.
Good question. My question is, with these 2 clocks, this calculated clock, do we have in mind whatever dark matter signal or radiation with the coherence length is smaller than the saturation?
So there is, yes. So there's one aspect, obviously, you have to take into account. The separation gives you a certain time you have been sensitive, and that basically determines where you are sitting in the frequency range. And so what we will do is we will basically go to interrogation times of a second or 10 seconds, because that gives you effectively the mid-frequency range, because 1 second free fall interrogation time of the atoms gives me 1 second sensitivity for gravitational waves. If I have 10 seconds, like in a kilometer shaft, I get a tenth for the frequency. So that's basically how you have to optimize it. And the same frequency range will also be for gravitational waves. So by combining the two is basically we're using the optical clock frequency 698 in case of strontium, which is the one being used for optical clocks, to run an atom interferometer on it. And it has this enormous characteristics of enormously stable and clean, because that's what you need for the clocks to get the high precision. And it has also the enormous high lifetime of hundreds of seconds, which is really important. If you want to build a satellite experiment, you have to make sure that they stay coherent. So if you have 10 to the 7 meter separation, you have to make sure that the laser beam, when it arrives, the two atom interferometers are still in coherence. And that you can only do with the clock transition of strontium or ytterbium. These are the two we are looking into it. So that is basically the combination. We use the clock transition, and we run an atom interferometer sequence on that clock transition, instead of basically just calculating its frequency. Yes. No, we're still seeing the interference patterns like an atom interferometer, but we're running it on the clock transition. And that was then the paper, which is now a major breakthrough for us, because it's really the first demonstration that the technology works. Now the next step is we need to scale it up. And there's many different projects currently in the world which are really looking into this in great detail. So it's not just what we have done in the UK. For example, also our French colleagues look at atom interferometry, not with the clock transition, but an atom interferometry, in building currently a prototype. Our German colleagues have already built a 10-meter tower to do similar tests, what we have been planning. Our US colleagues, in which we are in partnership with, are also starting to build a 100-meter instrument currently at Fermilab. And last but not least, to mention, China has a very comprehensive program in Wuhan, where a lot of those technologies are being tested. And in fact, Chinese colleagues have come to our workshops many, many times, and there's a very good exchange of intellectual discussions on this. So there's a quite comprehensive program currently ongoing in the world. And all of those projects, which John Ellis and myself have realized, are all funded with, let me call it like this, 20 to 30 million currency units. You then take whatever currency you like. These days, they're mostly the same. So if you add this up, there is a program of more than 150 to 200 million currency units currently ongoing of developing this technology for fundamental physics. And one aspect I think we particle physicists are always very good in, and with Professor John Ellis from King's College London and CERN, we were starting that, was to basically build a collaboration that brings all of these stakeholders together. And that was the TVLBI proto collaboration, which by now has 57 institutions from 22 countries, and we keep growing to really build the international community which we need in order then to go towards very, very long baseline atom interferometers. But out of that, and this is now very concrete, came a proposal of building the first big experiment in Europe at large baseline atom interferometer, and that is at CERN. I have quite a bit of background at CERN myself. I have been a particle physicist, so we have been approaching the CERN management, but maybe I say a few words about CERN before. For those who are not familiar with CERN, CERN started out as a European particle physics laboratory in 1954, but today it truly has turned into a very international laboratory pursuing many different aspects of collider physics, but also very strong in computational aspects and so on. So there's many cooperation agreements, for example, also with the People's Republic of China, as you can see here. So there's a lot of things and activities currently happening in fundamental physics at CERN. And one of the aspects we are trying to do now at CERN is to broaden the technology portfolio to do fundamental physics. And for that reason, I have been proposing, together with colleagues, the ACE experiment, which is a long baseline atom interferometer facility at CERN. It will be installed in one of the LHC shafts, namely in PX46. It's a 140-meter shaft, as you can see here. I'll give you a bit more details later. And this is now in a very advanced stage with CERN management. We have been asked to write a technical proposal. So I give you a bit more about this. The core of ACE is really towards dark matter and fundamental physics. We won't be able to reach immediately gravitational wave sensitivity because for that you really need to scale up to the kilometer. But you have a comprehensive program in dark matter, and not just scalar dark matter. You can run atom interferometers in different configurations to get sensitivity to axon dark matter and also vector dark matter by combining different species. If there are questions, I'm happy to say more about this. But this is now the current state. So this is now the planning we have. So there is 140-meter shaft at the LHC. That's the support shaft at the interaction point 4. This is how it currently looks like. It's really a big shaft where things can be lowered down. And the idea is that we are basically carving out a small cross-section to install an atom interferometer, as you can see here. So this is the atom interferometer. This will be the atom sources. You're putting them every 10 meters to do different atom interferometer sequences to measure gravitational gradient noise. There will be an elevator, which basically is built around the experiment so you can easily access the atom sources. So that is a relatively small experiment with a small footprint, but has a lot of capability. So this is the gentlemen which are currently putting this forward. Some of you may know that man in the middle, John Ellis, who has been helping a lot to push this experiment forward. But by now the collaboration is more than 100 people, but these are the ones which have been in June 26, so very recently again visiting the shaft. So in the background down there, this is the shaft, which then goes 140 meters down there, and we will basically carve out that small cross section. Yes? The free fall, because the free fall time is the key. As I mentioned to you before, if I have 1 second of free fall time, I will measure a gravitational wave optimally for 1 second. If I have 10 seconds, I will measure my peak sensitivity at a 10th hertz. If I only have 10 centimeters, like it is when you're doing it parallel, so you have only this 10, 20 centimeter separation, you are in 1 or 2 or 3 hertz of sensitivity, or even 10. This is where laser interferometry is already strong. We need to go lower, and for that you need free fall time. But ultimately, you want to bring it to space because then you have as much free fall time as you like. Yes, so you have to make sure that there is one common laser beam which triggers the whole experiment, and this is basically where the coherence needs to stay. Yeah, absolutely. No. No, that's you know, there are 10-meter instrument. One has a 10-meter instrument, for example. You can show that there is no interference. There's enough space to do all of that. The free fall does not interfere. That's a technique which has been developed for many, many years now. So that's the possible timeline for ACE, which we're currently proposing. I don't want to go too much into the details, but would like to make sure that people do understand that this is not just one experiment, it's a facility. So you're using the atom interferometer to be upgradable. You can have different sequences to run. Like, for example, you run on the clock transition, you run with dual species, so you compare to different atoms with each other. You basically have different ways of optimizing the atom interferometer sequence. There's a lot of physics in that program. And with that physics, you are really able to measure all the prime candidates of ultralight dark matter over a very comprehensive parameter space. So this is what you could do with scalar ultralight dark matter. I've showed that to you before. So this is our baseline. This is our stretch goal for the ACE experiment. So this is basically for the coupling DME. This is for the electron coupling. So you can see that there is a lot of interesting parameter space you can cover with atom interferometry. Now, interesting is these limits here are atomic clocks. These are optical clocks. So that's basically the same baseline technology, but run as an optical clock. So you're measuring the variation of the fine structure constant, and therefore you deduce whether or not there was a dark matter candidate. What you could do is, and that's another thing we are planning, is basically to run atom interferometry consistently with the same atomic clocks and basically timestamp the two, so you would have sensitivity level that spans several orders of magnitude if you run the two together. So that's another thing we are currently looking into it, but you can clearly see the atom interferometer is in a different frequency range, and that frequency range, if you just translate that, basically is 10 to the minus the mid-frequency range, which is the free fall time of the atoms. Because what you're measuring there is something different. You're comparing two different clocks with each other, so you have to have two different clocks. One clock of one species doesn't work. So, for example, you're comparing a cesium clock with a strontium clock. They will have different coupling constants of the scalar dark matter to the clock. So you're comparing the two. But then the frequency, you're just calculating the frequency. This is on a much higher frequencies because the baseline is much smaller. So you are basically sitting in a completely different frequency range. Now, it doesn't look that dramatic, but this is a logarithmic scale. So you're basically at 10 to the minus 22 instead of 10 to the minus 16 in mass characteristics. So it's just a different setup of the experiment.
I'm just surprised by the 10 minus 22 because the time scale for the oscillation is actually pretty long.
So 10 to the minus 22, you're approaching basically the wavelengths of a galaxy. So that's the wavelengths of that candidate to be for galaxy, if that is what you mean. So this is where people say, is this still a good dark matter candidate? I don't know. But then other people say, actually, it's a very good dark matter candidate if it's more. So I'm an experimentalist. I don't want to have a break.
He said it's a good dark matter candidate.
There you go.
But that scalar is really it's the scalar, not the axis, not the pseudoscalar.
No, that's the scalar. I come to the pseudo. This is actually the next slide. That's the pseudoscalar. No, this one is the pure scalar. The one which I showed you before with the coupling. For axion sensitivity, you will have to do different runnings. And that's the one I'm coming to now. So the next phase of the experiment would be you're going to two different species of atoms. So you basically run, for example, strontium to different isotopes, but even better, you run strontium and ytterbium, which have a mass difference by a factor of 2 and different coupling to the different scenarios. And you compare them, like the two clocks, you compare the two different isotopes with each other in the atom in the 4-meter sequence. And with that, you can get access to vector dark matter, B minus L structure, as you can see here, really far down in new parameter space. But you can also start getting sensitivity, for example, to QZD axions, as you can see here, because of the difference of the way how you have the coupling constant to the two different isotopes. And that's the third running. This is basically just one atom in the 4-meter sequence, but you're using the full length of the 140 meters, you're launching it, and you're going in a full parabola, so you have maximal interrogation time. And with this one, you can basically then measure the axion-nucleon coupling relatively precisely, as you can see here. And it's quite interesting, which I only learned when I was writing the technical proposal, is for the axion-nucleon coupling, there's very limited laboratory experiments. There's a very small parameter space with laboratory experiments, but the rest is basically free and mostly covered by the supernova 1987 limits. Now, if you look at the supernova 1987 limits, it's very difficult to make a statistical judgment. What does it mean? Is it a 95% confidence level? What is it actually? And is it really even applicable? We don't know that. So a laboratory experiment like, for example, ACE, in its baseline, but also in its stretch goal, can easily cover that new parameter space and see whether or not there is really something or there is nothing. So it gives you new laboratory capabilities in a different operational mode. So these are the three main dark matter candidates with 3 different running modes ACE can address. There's more, which is parasitic interpretations. Obviously, you have more exotic dark matter candidates, like spin minus 2 mass candidates. They basically can be inferred from the scalar running. But what we also do, because that is something many of our theory colleagues have found interesting, is that we have included in the design of the vacuum chamber now a test mass. So you basically can push the atoms against the test mass very, very precisely, and therefore you can look for strained scalar forces. This is now projections, what you could do with a 10-meter instrument, but with a 100-meter instrument, we're still working on the projections, you can go even further. So there's a lot of interesting new physics scenarios you can cover with this kind of things. The last few minutes, let me just spend a bit more on gravitational waves. and what ACE could contribute. So this is again the landscape we're looking at it today. ACE would have the possibility to reach into this domain around 10 to the minus 19 in strain sensitivity. This is just barely making it into the interesting territory, but it is only a prototype. If I were to scale this to the kilometer length, if I were to scale this to the kilometer length, I can show you this later, then I basically would really go into the real interesting territory. Where are we now with the proposal of ACE? So this is end of July, or we are now even, I should have updated the slide in August. So that's the timeline CERN has enforced on us to basically get going. So that was to define the structure. We have drafted the technical proposal. We had to write the technical proposal, and now we're going to submit the technical proposal, which is being written. The submission of the technical proposal coincides with a big workshop that CERN asked us to organize. This will bring together the ACE community, and for the first time, for many people who come from the quantum technology development, like atomic clocks, atom interferometers, this will be their first visit to CERN. So we are really starting to build a new community here. So anyone who is interested to follow it even remotely, here's the link. You can register, and then you get access to the Zoom link. There will be lots of interesting discussions on the physics and the technology. This is where the technical proposal is today. I was still working on it this morning. We're almost done. It's 152 pages. It is unprecedented in its form of detail. I mean, no atom interferometer experiment ever has done that technical detail, but it's one of the requirements CERN has been giving us. So this is out there for many people to look at. There's a lot of interesting information of how the technology and how to build such an experiment. That is all available in this technical proposal, but it also has a very strong explanation on the science program, on the physics capabilities, and in fact, this is probably the part where we are learning the most now, that we're really looking at the facility, because theorists now come up with new ideas, we're having new developments, so that I'm pretty confident that we haven't really exhausted all the options yet such an experiment can bring. And again, this is something I just want to raise with the audience, that there's a lot of opportunities here. So this is ACE as a final summary, if you like. It's one facility. It has at least 3 very important science areas. There's one I didn't mention to you, is the precision physics. But in principle, with ACE, you can also measure the fine structure constant, unprecedentedly high precision. And you can also have a very, very precise, actually the most precise equivalence principle measurement by comparing the 2 different species of atoms with each other. I had not much time, but clearly it's dark matter, precision physics, and it is a pioneer for terrestrial access into a new frequency range for gravitational waves. If I have a few more minutes, I can say, do I have a few more minutes? If not, 5 minutes. I can say a bit more about space, because that is where I think that technology needs to end up. We're building that technology now on Earth. We are building up the TRL levels, technical readiness level. We're making very interesting experiments, but ultimately, that technology will unfold its full potential in space, because then I have unlimited free fall time. I can basically get the frequencies I like for gravitational waves or for dark matter, because the free fall time is not a limitation. So this is back to where I showed you before. And in 2019 already, we were designing for the European Space Agency call of Voyage 2050, a proposal which basically has 2 atom interferometers. They are being 2 atom interferometers, each of them hosted in one satellite. So there's an interrogation range. A satellite region will be like this for the atom interferometer. The separation between the 2 satellites will be around 4 times 10 to the 7 meters, so there's a lot of sensitivity coming from that. And if you calculate the speed of light and the amount of time you need to separate between the 2, this is where you need the long decoherence time of the atoms, namely the clock transition. That's very important, otherwise you will get out of sync. So that's a full developed white paper on how that thing could look like. We even made simulations for the orbits and everything. And that is currently under review with ESA. NASA also is interested in, but anybody knows that before that will fly, the earliest would be 2045. according to the schedules which we are looking at. So there is still a lot of time in between of a terrestrial program to be developed, but it's good that this is in the making. Now, why I'm saying this is because I feel that this technology in general for space is underappreciated at the moment, by both funding agencies, big funding agencies in the Western world, NASA and ESA. They're very risk-averse, but the technology has very interesting potentials that goes far beyond fundamental physics and actually with a much earlier application. And one of the aspects this technology could contribute to, simply by measuring very precisely the gravitational field of Earth, would be to Earth observation in general, but also to climate change, because one of the big problems, in my opinion, well, there's many problems, but one of the big problems is that we are actually having, as you can see here, this is a blot taking out of it. We have many different models, but we are having not announced, I mean, how climate change is evolving, but we are not having enough precise data to really constrain this model so that we really have predictive power of what's going to happen in the next 10, 20, 30 years. And the biggest problem for that is that the classical sensors which we currently have in space that measure the gravitational field of Earth and therefore give you a relatively precise map of what is called the equivalent water height. The equivalent water height is very important to determine many different aspects of changes, of climate changes, temperature changes. So there is a huge literature in Earth observation of how that can correlate to many different aspects. But the problem with this is that with the sensors we currently have up there, the classical sensors, because of their drift, you basically can't resolve Earth. That's actually a map of Earth. I will show you in a second for the water height we can measure. Now, if I were to bring the technology I'm building today in the lab into space, we could measure already, and that's 5 orders of magnitude worse than the technology we need for gravitational waves. We could already start resolving very, very precisely the equivalent water heights, much more precisely, and you can make this even better. So this is now atom interferometers we can build today, basically. And that would have a major change in the way how we are basically collecting data. And the big challenge is to bring this into space and to really make the technology space ready. And we are pushing and lobbying now with both ESA and NASA, but also now have approached SpaceX, for example, to really make more awareness that this technology is now really ripe for real-world application, not just for fundamental physics. And the thing we are developing in the lab can do a lot of good once being brought into space. So I just wanted to make this show. So we had a very nice workshop here quite some time ago, which Sean Ellis actually organized at King's College London. For those who are interested in this, much more on how water height translates into it. There was a lot of Earth scientists basically there who gave us guidance and advice. So this is basically the vision of 2045 for fundamental physics, bringing this experiment to space to really be able to see the beginning of the Big Bang with gravitational waves. There's many other physics aspects I haven't at all mentioned yet. There's a lot of things we're currently looking into, in particular when it comes to dark energy. The correlation between dark matter and dark energy in that field of ultralight dark matter is much closer than it is, for example, with WIMP paradigm. So there's a lot of interesting experimental correlations we're currently looking at. But in my opinion, this is a very exciting new research avenue that is ahead of us, and this quantum technology is now really ripe for the application of fundamental physics and real world in general. So I'll leave it here, I think. Thank you.
Thank you very much for the nice talk. We have questions?
I want to understand better the sensitivity to the axion. So the axion does not cause the fine structure constant to oscillate nor the electron mass. So you are probing which coupling? This is the coupling to.
Well, it depends what running scheme you're having. So if you're basically having well, I can go back. Well, maybe if you're having dual species, you have sensitivity to the standard QCD axion coupling, the FA.
Okay.
By simply comparing the two, you get some sensitivity out of it, and it depends then on what kind of two atoms you are comparing with. So you have the properties and so on. And then you have also the coupling to the nucleon. And that again is the spin structure
There's the
of
coupling
the
to the spin,
atoms.
yeah.
So for example, we would use strontium, which is 9.5. And you basically have this very long parabola, and you can observe how that basically is changing in its behavior, which would indicate a potential coupling of an axion field to the nucleon. So it's longer interrogation time is, as more sensitive you will be. But in a 140-meter shaft, the best you can do is a full parabola of 140 meters twice.
So that is the coupling of the nucleon spin
Yes, nucleon spin coupling.
to the spatial gradient of the axion.
Yes.
No?
And
And that causes, I see, so that causes an energy shift that you can actually
yes.
detect.
And you even can, if you would see a signal, then take another atom. For example, you would take ytterbium, which is spin 1/2, and you would repeat the whole sequence, and you would see if that makes sense or not.
Okay. But you also mentioned, I think, one of your slides, there are like two channels for the axion. One is the nucleon spin, coupling to the nucleon spin.
Right.
What is the other channel?
The other channel is when you compare to different atoms. This is the FA coupling, the standard FA coupling, which is to the gluon coupling,
This is the
basically.
coupling to the gluon.
To the
itself.
gluon, yes, yeah.
I see. So this you're looking for.
So that is for two dual species operation. There you
Okay.
get sensitivity to the coupling to the gluon. If you make that just one parabola thing, it's one sequence of atomic
Yes.
formula, then I get sensitivity to the nucleon's coupling.
Are you effectively looking for an oscillating electric dipole moment? Is that what
Yeah,
you're
so
looking for?
kind of, yes, yeah.
Okay.
Change in the, yes, exactly that. Mhm.
Do we have other questions? Okay, if not, I would like to ask you a question.
Oh, sure.
It seems like for particle physics, the approach is always making things bigger. I'm wondering, is this really the only path we have, or could you construct, let's say, for example, multiple not so big detectors and use cross correlation or something like that, and still reach comparable sensitivities? Or
So if you just talk about sensitivity, the answer would be yes. But if you talk about frequency,
yeah, but you said, for example, 10 meters is already enough. We
But-
don't need.
but
millions
the
of
10 meter
kilometers,
has
right?
the problem that I will only have a free fall time of whatever 10 meter gives you, maybe let's say 0.9 seconds, or let's make it a second. That means my frequency I'm sensitive to, both for dark matter or gravitational waves, is 1 hertz.
Okay.
That's what my maximum frequency is. If I can go to 100 meters, where I have, let's say, 10 seconds of free fall time, then I basically can see a gravitational wave that has a frequency, or a dark matter wave that has a frequency of 0.1 hertz. They can all be measured at the same level of sensitivity, strain sensitivity or sensitivity to the coupling, but they will be sitting in a different parameter space range.
Okay.
And the important aspect for gravitational waves in particular is to find a technology that can sit in the mid-frequency range. And for that, you will have to have at least 100 or even ideally a kilometer equivalent of interrogation time of a free fall, or you bring it to space, because then I have an infinite free fall and I
Yeah,
can
no, but
dial
that's
it
the point.
away.
Like when you go to space, you make it much, much bigger than you would need for the frequency. So
But that was just, I make it bigger because the sensitivity scales linearly with length.
okay,
So it's easier to just have two satellites and put them as further possible apart, because then I get higher sensitivity. I can also put them closer to each other, but then I will lose the sensitivity scaling. So it wouldn't be
okay, but I
an
could
advantage.
replace it by multiple.
You could do, but
detectors.
then the experiment will become more expensive because you will have to bring multiple satellites up.
Okay. Do you have other questions? If not, then let's thank Oliver again.
So we have to get a 15-minute break, and then we can come back for the third half of the session.
Very nice stuff. You should have come to Virgo to visit, but anyway. So we have the third leg now.
Yeah, actually, we are thinking of combining.
No, but third is richer, so that makes sense.
The experiment is actually quite cheap.
It's 15 million.
It would cost a lot more than that. But
万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京。怀柔燕栖，群贤毕至。
今天我们再次齐聚北京，共同见证国际基础科学大会开幕式。
在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家探索基础科学发展之未来。
I think it's wonderful to bring together people from many countries and many disciplines. That is always how mathematics and science in general have prospered. One person can solve one thing, another person solves another, and then they put the ideas together and they can solve something new.
I find the relations that have been discovered between quantum information theory and gravity to be quite fascinating. And if I had to guess where a breakthrough might be in the next 10 years, I might guess there.
I find that I have to have the conversation in my brain, so you have to find out enough about the other field that you can start thinking about it. So it means you have to invest a lot of time in understanding enough about the other field that you can say something.
2026年首次颁发基础科学奖章，以9位科学巨匠命名。大会颁发前沿科学奖，世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
We are very happy to see the best minds come together to discuss the forefront of all the subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
这是基础科学的盛大聚会，这是一场顶尖的智慧交锋，让我们以基础科学之光点亮人类的未来。
Welcome to ICBS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to ICBS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to ICBS.
Welcome
to ICBS.
万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京。怀柔燕栖，群贤毕至。
今天我们再次齐聚北京，共同见证国际基础科学大会开幕式。
在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家探索基础科学发展之未来。
I think it's wonderful to bring together people from many countries and many disciplines. That is always how mathematics and science in general have prospered. One person can solve one thing, another person solves another, and then they put the ideas together and they can solve something new.
I find the relations that have been discovered between quantum information theory and gravity to be quite fascinating. And if I had to guess where our breakthrough might be in the next 10 years, I might guess there.
I find that I have to have the conversation in my brain, so you have to find out enough about the other field that you can start thinking about it. So it means you have to invest a lot of time in understanding enough about the other field that you can say something.
2026年首次颁发基础科学奖章，以9位科学巨匠命名。大会颁发前沿科学奖，世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
We are very happy to see the best minds come together to discuss the forefront of all the subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
这是基础科学的盛大聚会，这是一场顶尖的智慧交锋，让我们以基础科学之光点亮人类的未来。
Welcome to ICBS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to ICPS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to
Welcome to
ICBS.
ICBS.
Welcome to ICBS.
万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京。怀柔宴期，群贤毕至。
今天我们再次齐聚北京，共同见证国际基础科学大会开幕式。
在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家探索基础科学发展之未来。
I think it's wonderful to bring together people from many countries and many disciplines. That is always how mathematics and science in general have prospered. One person can solve one thing, another person solves another, and then they put the ideas together and they can solve something new.
I find the relations that have been discovered between quantum information theory and gravity to be quite fascinating. And if I had to guess where our breakthrough might be in the next 10 years, I might guess there.
I find that I have to have the conversation in my brain, so you have to find out enough about the other field that you can start thinking about it. So it means you have to invest a lot of time in understanding enough about the other field that you can say something.
2026年首次颁发基础科学奖章，以9位科学巨匠命名。大会颁发前沿科学奖，世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
We are very happy to see the best minds come together to discuss the forefront of all the subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。
Welcome to ICBS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to ICPS.
Welcome to ICBS.
Okay, welcome to the ICBS.
Welcome to ICBS.
Welcome to
Welcome
ICBS.
to ICBS.
万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京。怀柔宴期，群贤毕至。
今天我们再次齐聚北京，共同见证国际基础科学大会开幕式。
在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程3大基础科学领域，邀请全球顶尖科学家探索基础科学发展之未来。
I think it's wonderful to bring together people from many countries and many disciplines. That is always how mathematics and science in general have prospered. One person can solve one thing, another person solves another, and then they put the ideas together and they can solve something new.
I find the
So, hello everyone, and welcome to the last talk of today's session by, Subir Sarkar. Sorry.
It means to go up in Spanish.
Yes. Who is going to talk about a challenge to the standard cosmological model. So let's welcome Subir.
Okay, so I realize you have various different backgrounds, so this is going to be quite a gentle talk
very little technical details, but I also know there are some cosmologists in the audience, so hopefully they will hear something interesting. So this is a depiction of our standard model of cosmology today, which, as a previous speaker said, is a universe dominated by a cosmological constant. And what I'm more highlighting here is the formation of structure in such a universe. This is from a Hubble 10-body simulation. And the point is to illustrate that this universe is meant to be isotropic and homogeneous statistically. Of course, there is a great deal of structure, this so-called cosmic web of galaxies and clusters and superclusters. But the reason it is isotropic is because that was the initial condition. That was the assumption that was made in doing this simulation. So what I'm going to do in this talk is to be guided by this gentleman here, Dennis Sharma, who in fact kind of introduced cosmology into physics departments in the UK from mathematics departments. And he said this in a book back in the 70s, that before we start asking the deep questions in cosmology, maybe we should first ask, what is the universe actually like? In other words, use data to determine our model of the universe, rather than base it on philosophical principles. So just a quick reminder that this is not the first standard cosmological model in the history of humankind. Every culture in history has had a standard model. And this one is the one in Europe that actually, you can see, it held fast for 2,000 years. And it was very influential because it decreed that we are at the center of the universe and the planets go around us, and then there is the so-called fixed sphere, the primum mobile of the stars. And nothing should change in the sky. So Europeans did not even record the supernovae that were appearing in the sky. It was recorded by the Chinese, the Koreans, the Japanese, even the Native Americans, but not in Europe. Nevertheless, this finally gave way, as we all know, in the Copernican revolution. But actually all that happened was that the sun and the earth changed places. Everything else remained the same. Okay? And it wasn't until much later, as you know, that we actually had a modern idea of the dynamics that governs the motion of the planets. But let me fast forward 4 centuries to when Einstein developed theory of general relativity and the first cosmological models were constructed, starting with his paper in 1917. But I really date the standard model of today back to Friedman, which was 1921. Paper was published the following year. And of course, Lemaitre, who introduced the hot Big Bang, right? And we have moved one step more, and this Copernican principle, as it is called, that we are not the center of the universe, is now being used to demote the sun also from being at the center. So in this universe, everybody is the center. Now, the reason why it is important to bring some philosophy into cosmology, why it is not like the other sciences, is because, as George Ellis has been emphasizing over the years, we observe the universe from our particular world line. So we only see back along our past light cone. And of course, we see what's within it. We can't move somewhere else in the universe and construct another light cone and ask if we are seeing the same thing from there as we see from here. So we must make an assumption about what other observers, say Hubble distance away, would see. And this assumption goes by the name of the cosmological principle, which was actually formulated by Milne, who was the professor of mathematics at Oxford. But in fact, it already was implicit in the work of Einstein and Friedman earlier. And it seems to make sense. The universe must appear to be the same to all observers. You know, it's kind of, we're not giving ourselves any special position, very reasonable. But that wasn't enough for our spin-out company in Cambridge, where they said, this is too restricted. Milne has used a restricted form of the cosmological principle. You know, we are saying we are not special in space, but we are still special in time. So they say, let's go one step further. We are not special in time either, right? So in fact, Bondi said, Milne has done away with geography, but we'll do away with history, right? And that was the basis of the so-called perfect cosmological principle, that our aspect is independent of both space and time. And this, as you know, was the basis for the steady-state theory of the universe. But it took one observation to kill that, stone dead. And that was the discovery that the sky is covered with radiation from a hot, dense past. And although this discovery was made in the 60s, and by the way, Dennis Sharma, I learned from Roger Penrose, immediately recanted. He said, right, then I'm done with the steady state. But to be fair, it took until 1991 for it to be really destroyed, because only then we measured the spectrum and found it to be so close to a black body that you can't possibly make such a radiation by scattering starlight or something else and turning it into microwaves. You need such a large optical depth in the scatterers that essentially they would blot out your view of the universe. The only way to reconcile that spectrum with the universe that we see is to put it back at high redshifts in the past. And that's, in fact, the Big Bang model. So the perfect cosmological principle died there, but what about the not so perfect cosmological principle? Now that lived on. We still have it implicit in our model today, right? And the real reason for that, I think I like this quote from Weinberg's textbook, which is where I learned cosmology. Not that this principle is surely correct, but it allows us to make use of the extremely limited data provided by astronomy, right? And this he was writing in 1972. But he said, if the data will not fit into this framework, we'll be able to conclude that either the cosmological principle or the principle of equivalence is wrong. Nothing could be more interesting, right? And I don't know why, but the community seems to have entirely forgotten this, as you'll see. So let's first say what the standard cosmological model is, which embodies this principle. So the principle basically then says that space-time can be described by a maximally symmetric metric, the Robertson-Walker metric, and we have relativity to describe the dynamics, and we populate this universe with ideal fluids in the same spirit as saying that it is isotropic and homogeneous. So here is the Friedmann-Lemaitre-Robertson-Walker metric, which I have written suggestively like a Minkowski metric by not writing it in terms of time, t, but rather in terms of conformal time, because the only dynamical factor in the Friedmann, this universe is the stretch factor, the scale factor by which you are stretching space-time. And if I absorb that here, then I can make it look like it is Minkowski. But actually, the Robertson-Walker metric is not Minkowski even at infinity. But having got a metric, I can construct, as you know, the usual tensor, the Riemann tensor. I can construct the Ricci scalar, curvature, etc., and relate that all to the energy momentum tensor via Newton's constant. And this is, now, these all run from 1 to 4, so there are 16 equations, but it is symmetric, so it has to be 10 equations. So there are 10 coupled equations, and that would be impossible for us to solve unless we assume this degree of symmetry, in which case we get just one simple equation that an undergraduate can solve. And this is really why this model is so popular. It is calculable. And here we have the change of the scale factor is given just by the energy density of matter, the curvature of spatial sections, and a cosmological constant. And if I divide through by h squared, then I can write it in a suggestive way as in terms of the fraction and energy densities of the matter, the curvature, and lambda, where they are defined by just dividing by 3h squared by 8 pi g, as here. And the redshift, as you know, is just the change in the scale factor from the time of emission to the time of observation, suitably normalized. And all this now then boils down to a simple sum rule, 1 equals omega matter plus omega curvature plus omega lambda. And this is the essence of the standard model, right? Now, actually, there is a second equation, which is for the acceleration of the scale factor, and that has the right-hand side, the total gravitating energy density, which is not just rho, but also 3 times the pressure. Pressure is kinetic energy, that is also energy density. And now comes the interesting part. If this was just matter, as it was initially thought to be, dust, non-relativistic particles, then I just have rho matter, and it's got 0 pressure, so the thing is negative. It's the universe is decelerating. However, this T mu nu on the right-hand side, it was realized in the 1930s that the things that we call particles are excitations of fields, quantum fields. And Pauli realized that therefore the 0-point energy of those fields contributes to T mu nu. And in fact, because the thing has to be Lorentz invariant, the pressure is the negative of the energy density. And what that means is that this term can overcome this term here and change the sign in front, so you can get an accelerating universe if the vacuum energy density comes to dominate. So now this lambda that we are talking about here in these equations is the sum of this bare lambda from the geometrical part here. This term must always be there because it reflects the underlying general coordinate invariance, right? It's not anybody's choice whether you have to have the term or not. Now, T mu nu also has a similar term in it. It's a so-called super-renormalizable term in the Lagrangian, and the two add together. So the lambda that enters into cosmology is the sum of two terms which don't know anything about each other. I mean, unless you define them on a specific background. In general, they're totally independent. And yet, they have to add up to give you something which is of order h naught squared, because omega lambda can at most be of order 1. So you see the scale of lambda is being set here simply by the framework of the model in which you are putting the universe. There's only one parameter here with dimensions, which is this expansion rate. And therefore, you are essentially forcing the lambda that you have defined thus to take on a value of order h naught squared. It can't be much more than that. In fact, observationally, as you'll see, it turns out to be 2 times h naught squared, right? That's the actual scale of lambda, neither a fundamental quantity nor a constant. Now, how did this become today's standard cosmological model? Because we use this sum rule. So this is something that maybe not all of you might appreciate. You think there is a load of observations and they all have measured lambda. Actually, they have not. It's mostly inferred from this sum rule. The bit that is actually directly proportional to omega lambda is this expansion rate, the Hubble diagram of objects. And in fact, we use supernovae because we can see them right across the universe. And what that measures is 0.8 times omega matter minus 0.6 times omega lambda. I'll show you why. And that turned out to be a negative number. Okay. Then you have these observations of the microwave background, and these spots are about a degree in size. So if I do a power spectrum and expand in multipoles, the corresponding multipole is about 200. And that is actually the causal horizon on the last scattering surface. I forgot to emphasize that in the last slide. That's the maximum distance 2 points can be connected causally. That's why all the action is on degree scales. On scales larger than a degree, you can't have any causal astrophysical interaction, so that has to be laid down as an initial condition, and we usually invoke something like inflation to do that. Now, that peak position is proportional to square root of omega times k, and the fact that it is there tells us that omega k is close to 0. In more detail, it's actually degenerate to the assumed Hubble parameter today. Okay, so none of these quantities are determined by themselves. They're always degenerate to something else which you have to assume. And then you measure things like the same oscillations in the photons are also imprinted on the baryons. Now that is a much smaller amplitude. This is only a 1% effect rather than a 100% effect. And these are the baryonic acoustic oscillations, originally called the Sakharov oscillations because he first realized they would be there. And that tells us this omega matter. So you're used to this kind of plots where people show omega lambda on this side, omega matter on this side, and the supernova data is this diagonal here, and the microwave background data is this diagonal here, and they all intersect, and the BAO, whatever, lensing, cluster baryon fraction, all these things go through there. So they pick out this point here. And as I said, you're not directly measuring omega lambda except in the supernovae, right? CMB does not measure lambda. Baryon acoustic oscillations don't measure lambda. They assume the lambda CDM standard model framework to interpret the data, and they fit lambda. And the omega lambda turns out to be 0.7, and that, as I said, corresponds to lambda being about 2 times h naught squared. And h naught, for a particle physicist, is an infrared scale. H naught is inverse is 10 to the 28 centimeters. That corresponds to 10 to the minus 42 GeV. Okay? And the only other scale, of course, is Newton's constant, which is the Planck scale, 10 to the 19. So it's not surprising that if I write down this omega lambda in Planck units, divide by 8 pi g, which is multiplying by Planck mass square, then I get something which is the geometric mean of 10 to the minus 42 and 10 to the 19, which is 10 to the minus 12 GeV. And that's 10 to the minus 3 electron volts, which is the energy density or temperature of the microwave background. This is not a coincidence. This is, in fact, built in the way that we did this calculation. So the question I might ask at this point, because one always wants to know for a fundamental physics, where do the numbers come from? What is the scale of the problem? What sets it? The only scale in this problem is h naught. So do we infer lambda of order h naught square simply because h naught is the only length scale in the framework, right? Now, let's ask from a particle physics point of view, what do we know about lambda? Well, we have a standard model, everybody knows this. I've written it in schematic form with phi, these are the fermions, this is the Higgs field, and F are the gauge fields, and it's a beautiful theory, perhaps the greatest scientific creation of the last century apart from general relativity. And you all know that we are trying to now determine this potential of the Higgs boson at the LHC. But some of you also know that this is just the renormalizable part. I can also add an infinite number of terms which are of dimension more than 4, but which therefore have some power of a mass scale in the denominator. So this is the so-called effective field theory framework. This theory is valid only up to some energy scale m, and all the physics which violates the symmetries of the standard model, for example, lepton number to give a neutrino mass, or violates baryon number to cause proton decay or flavor changing currents, these are all suppressed by some high power of a cutoff, which explains why we don't see them or why we think they're so small, like neutrino mass. But there are two operators which people don't like to talk about because they're embarrassing. Now, the one that we have heard most about is this one here. If this phi is a point particle, if it is a fundamental boson, then the Higgs will get a correction to its mass from everything in the vacuum. So, for example, it will couple to a top quark, and it will get a correction to its mass, which is then proportional to the top quark-Ikawa coupling, and it goes now as the square of the cutoff. Now, this problem isn't there for an electron, because electron has chiral symmetry. In that case, there is a cancellation, which means that the cutoff only goes as log of the m rather than m square. That's the difference. A fundamental scalar like the Higgs does not have chiral symmetry to protect it. So then you have to think of solve this problem as to why the Higgs mass is so light. For example, supersymmetry is very popular. There you couple the Higgs to the Higgsino, which is a fermionic partner whose mass is protected by chiral symmetry. But the other option, of course, is to say this phi is not a fundamental particle, it's composite. But to date, as we heard from Yifang this morning, we don't see any indication of the Higgs boson being anything other than fundamental. It would be extremely amazing if it actually was fundamental, but we'll see. Only experiment can tell. We should really realize that our theoretical prejudices are there to be tested by experiment. Okay, we all have ideas, but ultimately data should call the shots. Now, this first term, which people don't talk about, is a measure of the vacuum energy in the standard model. Now, strictly speaking, you know that you can't actually measure absolute energies. You can only measure differences, right? I can always set a counter term to cancel this out to any order I like. But order of mag, in terms of the dimension of the problem, this will be of order m to the 4, and if m is of order a TeV, then I should expect a vacuum energy of about 10 to the 60 times the number that I gave you in the last slide, which is clearly a bit of a problem. So in other words, as the universe cooled down from the Planck scale, or whatever, as soon as it reaches 100 GeV, the thermal bath has disappeared. Only thing that is left is this m to the 4. And at that point, depending on the sign of this cosmological constant here, you should either collapse back to the Big Bang or go into eternal inflation. You cannot, expand slowly to make a huge old universe. Now, Pauli recognized this problem, as did Zeldovich, and he just asserted well, it's clear that the 0-point energy doesn't produce gravitational field. In fact, he did a little calculation about how the universe would not even reach to the moon based on the vacuum energy in electrodynamics. He was, of course, at the time they didn't know about electric theory. But it's the basic idea he got right? There's a problem. But Einstein tells us that all energy density should couple to the gravitational field. So there's a problem here. And this problem has not been solved. Okay, it's been nearly a century, it has not been solved. Instead, we have this claim by the astronomers that we have a lambda in the vacuum. Now, is there any way to test it in the lab? Well, what does that scale of 10 to the minus 3V correspond to? It corresponds to about 0.1 millimeters. So you might expect that if it is something to do with gravity, then there will be a change in the law of gravity around about 0.1 millimeter, 100 microns. So you might test for that experimentally. Let's just do some parameterization in terms of some kind of Iguawa-like force and ask if we can limit this. And here are some very careful experiments done by people using Cavendish balance kind of thing. And you can see here, this is the dark energy scale, and this is where you would expect this to be of order 1. The bounds are already a factor of 10 below it and going down further. But people haven't given up. I mean, Kumrun Wafa, the last time I heard him talk, was saying that there would be a change in the law of gravity at, I think he said 38 microns. And then in the subsequent talk, when they had actually gone down to 38 microns, he has brought it down a bit further. But at some point, you can't move it further, right? So at that time, those models should be ruled out. But the point is that all these proposed modifications of gravity, like, chameleon mechanism, symmetron, etc., all these things have so far not shown any indication of actually being, appearing in any laboratory experiment like this. You can, of course, make up whatever you like, but like I said, ultimately data will have to show. So why do we like the lambda CDM model so much in spite of all this, complete lack of any physical basis? Because it gives you a framework to understand how structure is formed in the universe. That's personally why I like it. So these are the fluctuations in the microwave background, which we don't know where they came from. We assume something created this roughly scale invariant spectrum of density perturbations. But we believe that they can grow into the structure that we see today. This is a redshift of 1,000. Here we are at a redshift today is 0. In this time, if you want them to grow into this structure, you actually cannot manage just with baryonic matter. You need about 6 times more matter that doesn't couple to radiation, so-called dark matter, in order to support the growth of the fluctuations. And that really is the most powerful argument for dark matter, because all these rotation curves and things that you hear about, that in principle can be mimicked by other means. This is something that alternative models find harder to do. And this picture basically tells us that we therefore have a full scheme. So you might want to enlarge your concept of the standard model to include something that created the perturbations. They are assumed to have a Gaussian random field. Why? Because it's kind of circular, because the models of inflation involve a very minimally coupled scalar field, which has no interactions, and therefore the fluctuations are basically Gaussian. So anyway, the whole thing holds together, even though it's not really logically airtight. And these perturbations can basically grow into what we see. This is the idea. Now, that means that today's universe is, in fact, inhomogeneous, and that is what we find it to be. So this is a map of our local universe. It is in velocity units, because that's how astronomers actually measure distances, right? So if you roughly divide by 70 kilometers per second per megaparsec, you get an idea of how far out this is. This is 15,000 kilometers, so this is about 200 megaparsecs, right? And we are at the center of the picture, and these fine lines that you see are meant to indicate our local velocities. So we are flowing towards the Shapley supercluster, and there might be a void on this side which is in fact repelling us. This is from something called the Cosmic Flows Tree Survey, led by Brent Tully at Hawaii for many years. And what is being plotted here is the peculiar velocity. So our velocity in the Hubble expansion is h0 times d, but we are not actually in the Hubble expansion. In fact, we are falling towards Andromeda, our nearest neighbor, and both of us are moving in one direction towards Shapley. because of inhomogeneity. The Hubble expansion happens only in the idealized isotropic and homogeneous universe. So the idea is that if I average out to sufficiently large scales, then I should get to that ideal universe. Now, if I map the universe out to further distances, this is from the Sloan Digital Sky Survey, it goes out to about 600-700 megaparsecs, and you see this cosmic web, beautiful. That's what makes us think that we're on the right track with this theory of structure formation. But what it also means is that we have to worry about who we are in this picture. First of all, you clearly can't approximate this universe as homogeneous, and yet many analyses of data which are local assume still the Robertson-Walker metric, which is clearly inapplicable. Should we assume that we are typical observers? Does it not matter if you're in a high-density region or a low-density region? That would surely affect what we see and what we experience. I mean, everything is local. The gravity responds to the local matter energy density. Can we assume that all directions are equivalent? If I look in this direction, would I see the same thing as if I look in this direction? Along our past light cone, the formation of structure would surely determine exactly how the null geodesics behave. Now, these questions are almost never asked in cosmology. In cosmic microwave background analysis, it has been recognized that there is something called cosmic variance. If you're in a random Gaussian field, it does matter where you are located. So we are already, in some sense, violating the Copernican principle. We are recognizing that. The fact that we don't actually see the low multiples in the cosmic microwave background is ascribed to our special position. But let's not talk about the philosophical aspects, we won't get anywhere. Let's talk about what we can test observationally. So if you are actually being pulled by some local inhomogeneity, this should fall off as 1 over r as we go out to further and larger scales, and within a few hundred megaparsecs, according to the standard model of structure formation, we should get to the point where you have converged to the so-called cosmic microwave background frame. I'll show you that in a second. And at that point, the universe should be isotropic and homogeneous. So then we can actually use this Friedmann-Lemaitre-Robertson-Walker metric. What is this cosmic microwave background dipole? Well, this was actually predicted by Dennis Sharma as soon as the microwave background was discovered, because we astronomers had already worked out that we are not in the frame in which the universe is isotropic. We have a peculiar velocity of a few hundred kilometers per second. So in ratio to the speed of light, that's 10 to the minus 3. So we should see, as an observer moving at a few hundred kilometers per second through an isotropic bath of radiation, we should see a temperature anisotropy of about 10 to the minus 3. And this was seen. And this variation on the sky is beautifully described by this formula, which is a standard exercise in special relativity. It was first calculated by Jim Peebles and David Wilkinson. And this is what tells us that this fluctuation that you see here is not the same as those little fluctuations of 10 to the minus 5. This is 100 times bigger. This is a local effect. That's the story, right? Now, yes?
When you talk about the peculiar velocity, you then expect some redshift due to the motion, right?
Yes, 10 to the minus 3, very small.
But you could also have some redshift or blue shift from the gravitational potential we're in. Is this accounted into this peculiar velocity?
No, the peculiar velocity is response to the gravitational potential summed over everything. Okay, so basically that's to the extent that we look at only the visible matter, we assume it traces the dark matter, but it is a dynamic measure. The velocity is a dynamic measure. If we just go by what we see, we might get our accounting wrong, right? But you're talking about time dilation in hot, dense versus underdense regions. Well, in principle, when that only works when you do the full averaging over the metric, right? In detail, it will matter whether, for example, if I am sitting next to a black hole, obviously my photons will be time dilated. It is assumed that we are looking at a continuum so that that effect does not matter. It plays an important role in something called the timescape model of David Wilshire, where he claims that it can account for some of the effects I'm going to talk about. We'll come back to that. Right? So what I wanted to say is our motion is actually a lot more complicated than what this seems to indicate, because we are actually orbiting in a Milky Way and we are going in the opposite direction to this hotspot. So our real velocity is actually 620 kilometers per second. But about whatever 250 kilometers of that is being cancelled out because we are moving in the opposite direction. And this whole Milky Way, as I said, is in orbit around Andromeda, will merge in a few billion years. And the whole lot is moving coherently along with other members of the local group towards this, it says Hydra Centaurus here, it's an old plot. This is actually from George Smoot's Nobel lecture. He got half his Nobel Prize for discovering this. And this great attractor, as it was called, nobody has ever found this great attractor. It was thought to be the Shapley supercluster, but today we can see that our flow is extending beyond Shapley. It has not converged. And the further you go out, the more ridiculous it becomes, because in order to pull us at this kind of velocity, you need a sufficiently large mass. And the further away you put it, the more massive it has to be because of the 1/r² fall off. Right? So already we are at a point where we must assume that there is some object out there that we can't see, which has a mass of 10 to the 17 solar masses, which is as big as our local Lanakia supercluster. But okay, I mean, that makes us one suspicious about this whole story, but how do we test it? Always you should ask, how do we test it? We must be able to falsify it. So if this is true, then we should converge to the CMB frame by averaging on scales larger than something of order 100, 200 megaparsecs. Do we actually do that? Actually, people anticipating that the standard model is correct, already, whenever you measure something, you already do a Lorentz boost. You boost it in order to get to the frame in which the universe is meant to be isotropic and homogeneous, right? So it is being implicitly assumed that this picture is, that we are going to converge and everything is going to be fine. Does that actually happen? Well, here is the data which casts some doubt on that assumption. So here is the bulk flow that I'm talking about, and here is the scale of averaging. So there are some technical details about if you average with a top hat filter or a Gaussian filter, don't worry about that. This purple line is the expectation in the standard lambda CDM model. And this is the actual data, right, on what our local bulk flow is as a function of the scale. And as you see, as you go out, although there is agreement with the expectation on small scales, it starts becoming a problem. This actually was data that we analyzed. We used supernovae for the first time to try to determine the flow out at large distances. But the uncertainties are very large because, you see, this distance you can't determine from the redshift. You must measure it independently, because the redshift is not an indicator of distance if you're not in the Hubble expansion. So distance indicators are very uncertain in astronomy. And the best you can do is about 15-20% accuracy using some empirical correlations between how fast a galaxy is rotating and its luminosity, something called the Tully-Fisher relation for spirals. For elliptical galaxies, it's called the fundamental plane, so there's some jargon there. But this is the scale of the thing, and up to here, you could have said, I'm getting a little worried, but everything is within 2 sigma, so why worry? Well, new data suggests that there is reason to worry. This is the SDSS data point from 2022. It's already beyond 2 sigma, but the uncertainty is still large. You could still live with that. But then came Cosmic Flows 4. And Cosmic Flows 4 is definitely discrepant with this description. In fact, it even seems to suggest that the velocity is rising as you go to large scales. And if you ask formally, how discrepant is this with the standard model, the answer is 4 point something sigma. The probability of this happening in the standard model is something like 10 to the minus 4%, right? So at this point, you have to ask yourself, do I still believe in the lambda CDM model? And the answer for most people would be, oh, these measurements are uncertain, we don't know the distances, let's just wait for more data to come, and until that point, it'll be business as usual, right? Yes? They have slight deviations in direction, but within 10-20 degrees. So the SMAC, so there are some groups that have kind of got a label on their, so the SMAC bulk flow deviates by about 25 degrees from the CMB dipole. Another bulk flow that was constructed by a different group is about 15 degrees off from that. But I would say they're in the same quadrant of the sky. In fact, the flow direction might well change. Now why is this interesting? Well, Christos Sargas is a relativist in Thessaloniki, and he's been saying for quite some time that if we are embedded in a deep bulk flow, which is this yellow region here, then we would not be an inertial observer or a typical cosmological co-moving observer. We would be what George Ellis had called a tilted observer. A tilted observer, when they interpret measurements, they have to take into account, ought to take into account the energy momentum being carried by the flow itself, right? You have to really should solve the Raychaudhuri equation, which is what Sargas and his collaborators do. And what they claim is that in that case, such an observer, when they measure the so-called deceleration parameter, the usual term will have a second term with the opposite sign here, depending on whether the flow is converging or diverging. And this term, in principle, can become larger than this term and reverse the sign of this, right? So it turns out that our local flow is actually contracting as far as we can tell. The data are very scatty. We just definitely need more there. But this raises the possibility that we might see acceleration even though the universe is decelerating because we are tilted observers in a bulk flow. So I first heard Sargas give a talk in 2010 or 11 in, somewhere in Greece, in Ioannina, and I said, can you predict how big this number is? And he's a relativist. He says, like, I need to know the shear and of the bulk. I said, look, nobody has measured all that stuff, right? What can you actually calculate? So we made some rough estimates, and they're all over the place. I said, but surely a clear signature is, if this acceleration that we are seeing is some kind of a illusion, this bulk flow, then it must be only along the bulk. It is directionally correlated. And he said, yes. In fact, he says that here. Such a dipole anisotropy would be lie close to the one. It really doesn't mean the term. It means the hotspot in the microwave background, right? So now, this was, of course, some years after the cosmic acceleration had already been claimed by two groups, not quite independent. They had a key member in common, who were looking at type 1a supernovae, which are events which are something to do with white dwarfs around the Chandrasekhar mass. That's what people say. In more detail, it turns out the stories can be more complicated than that. There is no standard model of type 1a supernovae. And their light curves are, as you see here, show wide variation. And these things, labels here, correspond to the band in which they're measured. The real advance that was made in the field is that people started using CCD cameras to monitor the sky. And what that means is that when a supernova goes off, then you can go back a few weeks earlier and ask what was the flux at that point. So you get the rise time, and you get the width of the light curve. And that's important, because without that, they would not be usable as for cosmology. Right? Now, the claim that was first made by these groups, that was in 98, 1999, they were looking at this magnitude as a function of the redshift, and the claim was that you are seeing these points inconsistent with the decelerating universe, which is this line here. They are all above it, and they claimed that there was an evidence, therefore, for acceleration, right? What was the actual measurement? The actual measurement, and I'm quoting here from the paper by the Supernova Cosmology Project, that the high redshift supernovae are about 15% fainter than you would expect them. So that's the actual measurement, right? 15%. So you don't need to be an experimentalist to know that, therefore, all your systematics must be under 15% if you really want to believe in that. Now, what do you do with the measurement like that? Well, you take that standard model that I talked about. These magnitudes of the supernovae are converted into something called luminosity distance, and that is related to all those omega matter, omega k, omega lambda. And so from this, you can work out that number, 0.8 times omega m minus 0.6 times omega lambda equals minus 0.2. Now, we decided first thing you do is to ask what direction were these guys looking at. Now, this is not in their papers. So we did some detective work with Mohammad Ramiz, who was my postdoc at the time. And he actually established that most of the supernovae that were being looked at by these two groups, about 50 each, were actually very close to the CMB dipole direction, right, as is shown in this map here. So it is, you might ask, what would they have concluded had they actually looked all over the sky, or in particular in the opposite direction, where the universe might actually be decelerating. Now, we decided we had to wait until the full supernova data set was released, and that was not till 2014. And at that time, 740 supernovae from 4 different surveys were combined into something called the Joint Light Curve Analysis Catalog, and all analyzed according to the same light curve template, about which I can talk more later. And what we did was to do a cosmographic analysis. In other words, we don't have to assume a cosmological model. We just do a Taylor expansion of the luminosity distance in terms of the Hubble parameter, the deceleration parameter, the third term is called jerk, etc. The only innovation we made was to allow this Q naught to have a monopole component and a dipole component. And we had developed a maximum likelihood estimator, which then we let loose on the data, and it told us that actually the acceleration is mainly in that direction that you see here, close to the CMB dipole, and it is a lot bigger than the monopole, which is consistent with 0, very close to 0. And this really made me think that Sagas might be on the right track, okay? That the so-called acceleration due to lambda cannot be due to lambda if it is anisotropic, because lambda is a property, it's a number. It's a property of the vacuum. It has to be isotropic. Okay, so let me now tell you about 4 frames of reference, because our work was criticized because we are doing it in the heliocentric frame. So I know about frames as well. So that is the heliocentric frame. This is the CMB frame where you boost by 370 kilometers per second. And then there is a local group frame, which is 620 kilometers per second. And you can do one more thing. After having boosted to the CMB frame, you can correct for the peculiar velocities of the galaxies where the supernovae are as well, because they would also be coherent, and you need to account for that in the analysis. So these are the 4 frames that we'll be talking about. When we put out that paper, Adam Rees told Physics World, oh, these guys are using out-of-date data. We have newer data. So we have used their newer data. This is the Pantheon Plus catalog, which is the latest data set, 1700 supernovae. And you can see the redshift distribution here. And we find the same effect. The dipole of this deceleration parameter or acceleration parameter is here. And you can see that it is dominant until about a redshift of 0.1, which is a few hundred megaparsecs, where you expect the bulk flow to die out. And it is of opposite sign according to what frame you look at it in, for the reason that I gave you earlier, that we are actually moving backwards away from the CMB hotspot. So our real velocity in the local group frame is 620 kilometers per second. And this is telling us that it cannot be due to dark energy or lambda, right? And these are the directions. As you can tell, they're very scatty because we have small samples of supernovae. You'll need much larger samples in order to pin down the direction, but the story holds together. And this is the new part. We are doing tomography. We take redshift slices because we have enough supernovae that we have order 100 in each slice. So we can determine how this Q naught varies as a function of redshift. And you can see that it actually changes with redshift. So again, it cannot be due to lambda. A further nail in the coffin of lambda is a correction to the magnitudes of the supernovae, which has been suggested by Korean astronomers, who say that the magnitudes are actually correlated with the age of the progenitor white dwarfs. And of course, you don't measure that directly, you have to do it in a roundabout way, so there is a lot of argument about if that is being done correctly. But interestingly, if we take their suggested correction, then we have is a movement from the black points to the red points in this magnitude redshift diagram. And if I put that together, you can now see what is the effect. Here is lambda CDM, 0 dipole, a monopole of minus 0.5. And what we are actually finding is here. It's a positive Q naught, Q monopole, and a strong dipole. So in other words, we are actually now seeing deceleration rather than acceleration. The dipole is unaffected. the monopole changes sign. And therefore, this tells me that supernovae don't actually provide any evidence for acceleration. Now, at this point, many of you would be saying, aren't there independent evidence for dark energy? So just to have a short amount of time. So microwave background, you have all been told the CMB nails down dark energy. Well, here is the plot from the Planck collaboration, which shows a beautiful fit to the data indeed, and they have all these parameters they reduce from that, omega baryon, omega cold dark matter, optical depth to last scattering, spectral index of the spectrum, blah, blah. My question to you would be, where is the entry for lambda? There is no entry for lambda because the CMB is not sensitive to lambda. They determine omega lambda by subtracting from 1 omega matter and omega k. Okay? You can look at the paper, it's on page 37, you can check, right? And this is why this data does not directly tell you if there is lambda or not. Now, actually, for those who are experts here, there is a subtle effect called the late integrated Sachs-Wolf effect, which would come into play and induce a correlation between large-scale structure and the CMB after lambda comes to dominate the universe, because then the photons coming towards us, they fall into potential wells and climb out, and the two red shifts and blue shifts will not cancel once the potential is evolving. But that effect is of order half a microkelvin. It has not been detected convincingly so far. Daisy might be able to see it. Okay, now to cut a long story short. What do you mean the CMB data is isotropic? Yes, the fluctuations at the CMB are isotropic, that's correct. But that is not relevant to the supernovae. The supernovae are not at redshift of 1000. They're localized close to us. No, but the acceleration that we infer from supernovae is anisotropic. Okay, that is what's relevant to the question of whether lambda is accelerating the universe.
I don't see the logic. Like for example, we just keep the CMB data and then with this isotropic, we use the FLW formulation, which is lambda. What's the logic?
How do you know that that model is the correct description of today's universe? No, you're describing an universe at a redshift of 1000 when there was nothing around except for a diffuse background of radiation. Yeah. What relevance does that have to today's universe? No, I don't think you're getting the point there, but let me continue, we'll come back to that. So what I want to say is that all the evidence for dark energy from CMB, gravitational enhancing, baryon acoustic oscillations, it's all inferred assuming this FLRW metric. Right? So the whole thing rests on if the FLRW metric is actually correct. And this is a warning from Richard Tolman that basically, sure, let's carry on using the FLRW metric, but at some point, if we are dissatisfied on observational grounds with the results, then we should then consider whether this assumption is actually true. Okay? So let me just deal with that in the last 10 minutes. If you ask, pick up a textbook, this is Jim Peebles' nice book, and he says the distribution of radio sources is isotropic on the sky, right? Now, actually, that can't be true because the microwave background radiation is not actually isotropic on the sky. It has this dipole anisotropy, as I showed you. So this must also be anisotropic because that's just an effect of aberration of our movement. But you can't see that with 30,000 sources. This is from Green Bank, West Virginia. I always used to wonder what this streak was. It's actually the Milky Way because there are radio sources in the Milky Way. And these gaps are the regions that you can't see from West Virginia. This is going to be important in what follows. What is aberration? It is an effect that was actually found by Bradley. He was, in fact, the professor of astronomy at Oxford. So over 200 years before Einstein, he already worked out that the speed of light has to be finite. So that's why a star appears displaced from its actual position on the sky and by an angle which is calculated by this formula, which is actually a special relativistic formula. And of course, if you are looking at the microwave background radiation, that is a black body. But if you look at other sources, they typically have power law spectra. So in our boosted frame, we are going to be sampling a different part of the spectrum than the observer at rest. But this is all special relativity. To cut a long story short, I can put it together, and like Ellis and Baldwin, I can say that the dipole anisotropy is of order V by C cos theta, just like for the CMB. But there is a prefactor which has to do with these exponents of this flux spectrum and the number count cumulative distribution. So this is the actual effect. This is the isotropic bunch of objects, but if I'm moving in this direction, then I'll see them bunched at that end, and there will be a little sparer at this end. So I'll see a dipole anisotropy. I have exaggerated that effect because the real effect is of order 10 to the minus 3. In fact, if I take into account this prefactor, it becomes 5 10 to the minus 3. So that's a tiny effect. That's 0.05%. Sorry, 0.5%. Now, Ellis and Baldwin wrote this paper back in 1984, and they said if the standard interpretation of the dipole anisotropy is due to a peculiar velocity, then radio source counts must show a similar anisotropy. Baldwin was the head of the Cavendish Radio Astronomy Lab and about to undertake the Cambridge survey of radio sources. And they made a very prophetic statement. If the standards of rest determined by this two were to be in serious disagreement, then you would either have to give up the idea that the sources are at cosmological distances, or the interpretation of the CMB as relic radiation. I don't think either of these would be acceptable today. Or you have to give up the standard Friedman, Lemaitre, Robertson, Walker models. How does it fare? So in order to measure that such a small anisotropy, you need a million 10 to the square of that. A million sources only came about a few years ago, thanks to a chance meeting I had with an astronomer from the Naval Observatory in Washington, who was working on this WISE satellite, which was mapping the sky for many years in infrared wavelengths and bands. These are all the wavelengths in microns. And by doing color thing, they can separate quasars. So these are the really the accretion disks around the central objects which get heated up and emit in the infrared. And by measuring these and by putting a proper color cut, you can isolate them and you can make a flux cut, because the Ellis-Baldwin test requires that you are measuring the objects that are boosted above some flux threshold in the direction that you are going and correspondingly boosted below it in the backward direction. And you can look at the spectra of these objects and to look for various systematic effects. I don't have time to deal with that, but you have done all that. And we then get a map of these quasars on the sky. And very luckily, these redshifts of some of them have been measured by something called the EBOS project, Slow Digital Sky Survey. And you can see that the redshifts measured by spectroscopic methods are actually very precise. So the median redshift is over 1. They are at cosmological distances. This is to avoid the idea of a so-called clustering redshift. They can be very close to us. So here is the dipole that comes out of the quasars. And what I can now do is I can take that observed distribution of the spectral indices and the flux and randomly select from them in a Monte Carlo and do it 10 million times and generate the expectation for what amplitude and direction I should see according to the null hypothesis, which is the standard cosmological model, right? So we are doing frequent disk analysis. We know what the answer should be, and we are trying to falsify it. It turns out that the direction of the dipole is consistent with the CMB. That's the black star, and what we see is the triangle within the uncertainty. But the amplitude is not. This is the expected amplitude according to the standard cosmological model, and this is what we find. It is 5 sigma discrepant, right? And this is an issue because you cannot have any way in which this aberration effect can create a 5 times, double the amplitude that we see, unless the quasars are anisotropic in the frame in which the microwave background radiation is isotropic. Now, which one of them has an intrinsic dipole, we don't know. We don't know what we can say is that if we are moving with 370 kilometers per second, then we should see these quasars as isotropic in that frame. We go back and we looked at these radio sources from the NVSS survey. This is done at the Very Large Array in Socorro, New Mexico. And we mask it with the radio map of the galaxy. This is the 408 megahertz Haslam map, for those who know it. And we find that these two separately are consistent with each other, and subsequently other people have looked at new radio catalogs. They find a even more significant answer than we did. And when you put this together, these are like two experiments. This is like Atlas and this is like CMS, and they're both finding a discrepancy with the standard model, right? So a bit like the Higgs discovery, that gives us confidence that two independent experiments are giving us the same thing. And now we have crossed 5 sigma in this rejection of the standard model. So do I have 5 more minutes? Yeah.
Yes.
Thank you. Now, I want to address some problems. So obviously, this is the big deal. We are essentially saying the Friedman-Lemaitre-Robertson-Walker metric has been falsified, right? That would really mean going back to square one. And naturally, people don't want to accept this answer, right? They will raise all kinds of furious questions and say things like, the CMB looks isotropic, so why shouldn't I assume it? Because the matter distribution is not isotropic in the same frame. That's what really matters. Now, one opposition that was put up is that what we could be seeing is a clustering dipole. In other words, by random chance, one of these quasars might be very close to us in some particular direction and give us a large dipole because of that. This would have to be statistically unfortunate. Now, first of all, we know there are no quasars close to us because otherwise you'd be fried. Apart from that, you saw from the redshift distribution that they are actually 99% of them are over a few hundred megaparsecs away. But, and then some people said, oh, you guys are doing frequentist analysis. We should do it by Bayesian method. That's inherently better. But actually, if you do it, you get an even higher significance. So that did not work. Now, let me show you, and also, as I said, independent analysis recently done by Dominic Schwartz and collaborators finds 5.4 sigma evidence from radio data alone. By the way, all these papers are published in things like ABJ letters and physical review letters, etc. So, you can guess that they have been very rigorously peer reviewed. It typically takes us a long time to get them published because people raise all sorts of objections that you have to answer before it through. Then some people said, well, you're using special relativity. You live in a general relativistic universe. So you should calculate it properly in GR. Now, actually, a little physical intuition suggests it should not matter because locally space-time is flat. We are in special relativity. But okay, we did the proper analysis, looked at the null bundle, etc., and we calculated this dipole, and we find exactly the same answer that Ellis and Baldwin found here, plus a little correction. And that correction depends on the number distribution of the sources. And when we plug that in, then it turns out to be less than 1 part in a 10,000 correction. So that is negligible. And then some people said the evolution of those distant objects will affect our answer. And the counter to that, as was shown by Sebastian von Hauseger, my postdoc, is that it doesn't matter at all. And this is something that Jim Peoples himself said at a meeting that we organized in London. So here, we have a dipole in quasars, we have a dipole in radio sources. They are consistent with the direction of the CMB dipole within uncertainties, but the amplitudes are not consistent with the expectation from the standard model. And we have therefore 2 independent bodies of data which say that we are violating this FLRW assumption. And this is not dependent on the cut we apply in the magnitude and the power spectrum. Now, this is interesting. We now have enough data that we can do a power spectrum of the multipoles on the sky, not just the dipole. And we find that the high multipoles, the small angles, are actually consistent with the standard model lambda CDM expectation. But if you extrapolate it to the dipole, then you see that what you expect for the clustering dipole, that's what it is a lot smaller than what you are actually measuring up there. Okay? And there is no other power here, which Douglas Scott and others were challenging us about. So there is no question of the dipole being contaminated due to leakage because we are masking the sky, which is true. If you mask the sky, then the multipoles are not really orthogonal anymore. But we have addressed that issue by doing this power spectrum. Okay, so let me move on to what happened? Sorry, I just have to. Excuse me. I seem to have got stuck before we get to the conclusions. Anyway, let me say it, I don't want to hold you up. So the bottom line is that we have a over 5 sigma evidence that the standard Friedman-Lemaitre-Robertson-Walker metric is not valid in the sense that you can't find a frame of reference in which both the radiation from the Big Bang and the matter distribution today in the universe are isotropic, okay? And this assumption is key to analysis of all cosmological data, including the data from the recent, for example, dark energy spectroscopic instrument, DAISY, which is actually looking at about 35% of the sky. And I finally managed to persuade them to look to see if within their data they have any anisotropy. It is detectable, turns out, but they have not done that. They instead choose to model their data in terms of a equation of state that varies with redshift and claim they have evolving dark energy. But the fact that the acceleration, which is the only direct effect of dark energy so far in the data, that itself is anisotropic, already, in my view, rules out anything to do with vacuum, right? Quite apart from the theoretical reasons why one might not believe that something at that energy scale has got anything to do with fundamental physics, the very fact that it is anisotropic must surely be convincing that it is a local effect and has nothing to do with the quantum vacuum. It's got nothing to do with scalar fields. It's got nothing to do with the cosmological constant. The cosmological constant is probably zero. We do not live in de Sitter space, attractive though it is, for many reasons. And we really must try to go back to the point where people like Weinberg and Tolman and others who were the pioneers in this field told us we should look once we draw conclusions from the data, making these simplified assumptions that are unpalatable. And I believe the assumption that we are dominated by a cosmological constant or vacuum energy at a scale of a milli-electron volt is very, very unpalatable because it is the biggest fine-tuning problem I know of in nature. And I think the least we should do is to look at the data to see if that conclusion is supported by it. Thank you.
Thank you very much for the talk. We can have one quick question.
Is that it?
Thank you, Subir. You talk about the acceleration dipole in the supernova data.
Yes.
Do you see the same dipole in the velocity from the same data?
In the velocity?
In the velocity. You can also
You mean
analyze
the local velocity?
just the peculiar motion from
the
same sample.
It is roughly in the same direction, within 20 degrees.
But if you interpret this as due to, again, some kind of bulk flow,
yes.
Do you actually get the same velocity?
It is aligned with the SMAC bulk flow. So as I said, the bulk flow direction, depending on who has analyzed the data, it's not always the same. Okay? Some people, in fact, determine the bulk flow by first constructing a mass model and then calculating the velocity field from that. Others try to measure the velocity field directly, right? The calculation would have to assume both irrotational motion, so no curl in the field, right? But it also, beyond the point where you have data, they assume lambda CDM. So, the more I look at it, the more of a can of worms it turns out to be, that people are often putting into their analysis assumptions about the very thing that they're meant to be testing. And I find this quite horrifying, frankly. Now, I recently had a online discussion with Scott Dodelson, who is also concerned about this because one of our ex-students, who is in fact in his department at Carnegie Mellon, had pointed out that of all the measurements of lambda published in the literature, an overwhelming number of them cluster within the right value, the one from WMAP, okay? You would expect only a third to be within 1 sigma, right? But they're actually 2/3, more than 2/3 are within 1 sigma. So there's clear evidence of confirmation bias. So in the more recent experiments like the dark energy survey, they have done a blind analysis to get beyond this. And in fact, the only way now you should do in cosmology is a blind analysis, right? But even there, with the dark energy survey, since you're an expert on this, let me say, it turns out that they actually saw an overall shear over the field that they looked at, which they then put to 0 by hand, because the universe must be isotropic, right? And this unexplained shear is about 6 times bigger than the systematic uncertainty that they estimate in their measurements. So, I mean, the problem is very deep. It's really become something that even seasoned observers do not seem to realize that this is actually not a good thing to do, that you can't simply keep assuming your answer when you are trying to determine some new fact about the world. Right? And the second problem I find in this field, as somebody coming from particle physics, is that whereas challenging the standard model is perfectly okay in particle physics, everybody does it every morning, right? Somehow in cosmology, it's like sacrilege. You are considered to be kind of, questioning the kind of, the reality of whatever. and I find that to be very surprising. And actually, now that I've got my slides back, let me just show you something that Jim Peebles said when we actually had a conference in London a couple of years ago, and he came and he gave a talk, and he wrote a review after that, and he says, this dipole anomaly which I've just described, I don't know how many of you had heard of this dipole anomaly? Really not very many, right? It is about as well established as the Hubble tension, yet the literature on the kinematic effect is much smaller than the hundreds of papers about Hubble tension in the ADS database. And then he says, I expect the difference is an inevitable consequence of the way we behave, which I thought was quite interesting for someone of his stature to say publicly, that there is this sociological effect where people focus on the dipole, on the Hubble tension, and don't mention the dipole anomaly, because this really means, I think they're worried they'll be out of a job. That's really the problem. Okay, so I think that's all I wanted to show. That is the slide that I couldn't show you earlier. Just wanted to mention that this has attracted some theoretical interest, and I hope it will attract others. And this is my summary, which I'll leave up there for you to look at.
Okay, we have to finish.